So he received recently his master's degree from the Electrical and Electronics Engineering Institute of the University of the Philippines, where he did some research during his internship on reinforcement learning for 3D reconstruction. So I came across his work in a conference, in the ECCV conference, where you presented it, and I found it very interesting. So that's why I invited him, and thank you very much for being here. And now the floor is yours.
Thank you very much, David, for that introduction. Let me just share my presentation slides. Can you see my slides?
Yes.
Yes.
Thank you very much. So I'm Daryl Peralta from the University of the Philippines, and I would like to thank first Sony CSL Paris for inviting me here. It's a pleasure to be able to have this opportunity to present our research to you guys. So my talk has a title of Next Best View Policy for 3D Reconstruction. I'm one of the authors of this paper together with my colleagues from the University of the Philippines. And as David mentioned, this research work was presented and published during the European Conference on Computer Vision Workshops last August 2020. And so my talk would include the whole research work for this paper, from the motivation to the ideas and algorithms to the results and the conclusions and even the future work. So today we have applications that demand 3D models. This include robotics, specifically autonomous vehicles. And these autonomous systems need 3D information or 3D representation of their 3D environment in order for them to safely navigate and safely and properly navigate. But not only 3D, but not only robotics, but also for virtual reality applications, augmented reality applications, and even normal game development. 3D models are highly in demand, and both the small ones, the small 3D models of objects, and even the large 3D models. So for this work, we are very interested, or our focus is to work on the technology that allows us to create 3D models of large buildings, such as this one on the right side of my slide. This 3D model is a real output of one of our experiments in our campus. This building was reconstructed using computer vision algorithms from the data that we gathered using aerial drones. And so these kinds of large 3D models of large buildings are not only useful for virtual reality or game development, but also for applications, potentially for applications like construction management. If you would see here, this is actually a building that was under construction during that time that we flew the drone and gathered the data. You would even see here the construction site where the workers are working to construct this building. And this kinds of technology allow project managers and engineers to better manage these kinds of construction projects. And I will be showing another 3D model. This was also from our experiments, and this is a real building inside our campus. The details, a very detailed 3D model of a large building. So these kinds of 3D models can be used for disaster risk management. When disasters come and we want to assess the health or the conditions of these buildings, this 3D geometry information represented digitally can help the personnel to assess the health of these buildings. So also for especially, or is more importantly, for those buildings that are historically and culturally important to us, such as what happened in Notre Dame in Paris, in the cathedral. So we want, if we have a digital 3D model of those structures that are important to us culturally, historically. It could help us restore them in case something bad happens to them. And so those are the applications of 3D models. But how do we really create these 3D models? No? So this is a well-studied problem and in computer vision, mainly because we human beings, we can easily infer the 3D structure of our environment. If I see an object, if I see a ball, for example, I can easily say that the ball has a shape of a sphere. But however, for computers, when we capture images, we lost the 3D information. We are left with the 2D data. 2D data composed of a matrix of numbers or pixels formed of pixels that we call monocular color images. So that problem of recovering that 3D data and the set of solutions to that is called in computer vision 3D reconstruction. So we can, it is possible to classify the solutions or the algorithms to this task based on their input data. The first type of these algorithms are those that are based from structure from motion. These are algorithms that creates 3D models only using monocular images. Another uh, track or another class of these algorithms are those that use depth information. Those are the depth-based algorithms, which were really prompted with the availability of commercial depth sensors and even LiDAR data. So, uh, so for our case, since we are very interested with the creation of large 3D models of outdoor structures, such as buildings, houses, uh, we are using drones to gather the input images. So to do that, we are using aerial drones. No? So most drones, what the sensor or the data gathering device that are available to them are monocular cameras. Since most commercial drones are normally used for photography, most of them has cameras. So I will be discussing one example pipeline of how this computer vision algorithm called structure from motion creates the 3D model of the scene captured by those images. So structure from motion, from the name itself, structure from motion, is both the problem and the set of solutions that allows computers to simultaneously estimate the structure or the 3D structure and at the same time the motion of the camera or the camera parameters. So from a set of input images, it can estimate both the structure, the 3D reconstruction, and the camera poses to be exact. So here is a block diagram of CallMap. That is a very famous open source SFM implementation based on the paper that they published in CVPR 2016. So just this SFM implementation, of course, will have variations depending on the implementation, but most of them would start with some corresponding search. So very important are the features in the images which are extracted and matched across frames. Then, of course, some geometric verification. Then it will go to steps that are compose the incremental 3D reconstruction part. So here we have image registration, triangulation to get the 3D location based on the camera poses. Then we have the well-known bundle adjustment, where we try to optimize the consistency in the 2D features and the estimated 3D model. So it's an optimization. That's why you would see a loop here with, of course, an outlier filtering until we minimize what we call a reprojection error. From there, once we have a consistent estimate of the camera poses and the position of the 3D feature points, 3D positions of the feature points, the final output of these algorithms are the 3D model, and not just the 3D model, but also the estimated camera poses of the 2D images. So that's the algorithm behind how we are able to create those 3D models, or that's the core algorithm behind those 3D models that I've shown before. But how do we apply them on drones? No? So just like I mentioned, this is a real footage. This is me. I'm piloting manually the drone. This is a real drone footage using a DJI drone. We are capturing frames here. No? So frames from around the target object. And again, from those image frames from multiple views, we will use a 3D reconstruction pipeline based on structure from motion to create the 3D model. But what is the problem that we've experienced? The main problem that we have been experiencing most of the time when we are using this methodology of flying the drone, capturing images, going back to the lab, because these algorithms are not really consumes computational resource. You cannot simply run them on board your drone. You would have to go to the lab or to somewhere that you have enough computational power to run this algorithm. And when you go back to the lab, run the algorithm, SFM algorithm with some multi-view stereo and texturing, you would see output like this, output with large holes in it. No? So you would, if you look here, you would see 3D model, a large hole underneath this object. Recall that the structure here is complete, but since our flight path, we're not able to capture those underneath the roof, the output has a large hole in it. And on the right side, this is another example, the one I showed previously. Before we were able to create that uh, highly detailed and high quality 3D model of these buildings, the initial output of our flight mission looks like this, a building with a large hole on top, mainly because of how we selected the viewpoints. So we were not able to capture the viewpoints on top. So how do we solve that? Why is it important? Because as I mentioned, you would go to the lab, you would run these algorithms, and you would discover that my data set is incomplete. So I have to return to the site. That's time consuming, that's computation resource consuming in terms of computational resources. And of course, power consuming because you're running computers, you are going to the site, consuming energy. So we want to contribute on how we can improve the way we do these things, the way we create 3D models, or the way we create large 3D models. So this is very similar to the problem of view planning in both in 3D reconstruction and in active vision. So this view planning problem is the problem of minimizing views to cover a target object. So that was mentioned first in this paper in CBPR 2017. And our idea is that this view planning problem of minimizing the views to cover a target can be accomplished by selecting the next best view. Excuse me, the next best view is a term that was introduced by another paper, which I will be discussing later. So the main problem here is that the manual view planning that a manual pilot would do, or even the off-the-shelf circular path where that is commonly available in commercial drones, where you point to the top of the roof and then the drone would circulate around it, results to incomplete 3D models. One intuitive way that you might think of how about just introducing redundancy? Let's just put in more images, more viewpoints. However, that approach would result to lengthening of the processing time. Since the more data you have, the more input you would have for the optimization algorithm inside the structure from motion. And that would lengthen the processing time. And so you're wasting computational resource. And also for our application, drones have very limited flight time. So we want to contribute in trying to address this problem, to have a better way of scanning using aerial drones. So as we've looked into the literature, of course, these are some possible ways that we've discovered. Of course, the circular path, this will be our baseline in our experiments. This is the most commonly available autonomous path that you can see in commercial drones, where the drone can now circulate around a point. You can target that point on top of a building or on top of a house. But as I mentioned, that will result to incomplete 3D models, and I will be showing that later. Some possible algorithms are those that propose information gain from a paper in ICRA by Eisler et al. They were also the one that introduced the term next best view. Also, some paper on proposed to use the surface reconstruction to assess the quality of the surface reconstruction to propose the next views, and even based on the point cloud. However, all of these are hand-engineered criteria in selecting the NBV. There are some learning-based methods, but most of them have low resolution or did not optimize the path. So with that problem of view planning and having incomplete 3D models and no way to have a more systematic approach to scanning houses and buildings, we ask the question, can an agent learn to scan a house efficiently by determining the NBV from monocular images? So this is the core idea or core question that we wanted to answer in this research work. Can we train an agent to learn that process of selecting the views to scan a house efficiently using simply monocular images? Why? Because monocular images are easily captured using the cameras available in most commercial drones. So to formulate this idea, we approximated the NBV selection process as a Markov decision process and applied reinforcement learning algorithms to find a policy that can select the NBV. So an RL algorithm trains a policy, and that policy was trained to select the next best view. And so we call that policy the next best view policy. And of course, since our application is 3D reconstruction, we call this NBV policy for 3D reconstruction. And so to implement this idea, I will just go through this, some synthetic environment, Unreal Engine. It allows us to create realistic scenes. And to go through that, the main contribution of this paper is ScanRL. This is the learning a next best view policy. And so this is the block diagram of ScanRL. You would see here, very common. If you're familiar with RL, this loop or this kind of block diagrams are common in RL algorithms. So I will start with the input or the raw input from your environment. So for our case, since we are working on the synthetic first to test this idea, we are rendering RGB images, color images from the Unreal Engine environment. And from there, we want to create the state. So these are the raw input images. And we want to, for the state, in RL, the state is the input to the policy that captures the information necessary for the policy to make its decision, take actions to perform some task. So here, our pre-processing functions is very simple, some resizing and some concatenation. And again, the reason why we are simply using images is because cameras are available in most drones. The pie here, the large pie here, is the policy. It's the one that takes the state and decides which action to take. So this should be A sub t is equal to pi of s, meaning the action at time step t is the output of the policy pi given state. So this is the one that we are training. This is the NBV policy. So how did we define or how did we set up the action? Now, for the action, we use the change in camera pose. We use the change in camera pose, the delta phi, delta phi, and delta psi. So we parameterize the pose to 3 degrees of freedom. So the theta is the azimuth angle. So to better illustrate that, this is the azimuth. It is very simple, a horizontal motion along the azimuth. Now for the phi, this is the elevation angle. So it's a vertical movement. And the psi is the distance from the origin. A very simple 3 degrees of freedom parameterization of the camera pose to simplify our setup first. Now we implemented both the discrete, so meaning this camera changes in camera poses are discrete, and also some continuous action space setup where the changes could be continuous. Why? Because discrete, it's more simpler and easier to learn, but we are also interested if it could possibly scale up to continuous action spaces where you have more freedom to position your drone. So now, once you take an action, once the policy takes an action, the drone or the camera would go to another position and depth images would be rendered. And from those depth images, we implemented a 3D reconstruction module where we create the point cloud 3D reconstruction. So for this, we implemented a depth fusion algorithm cited here. It generates 3D point cloud from depth images and camera poses. Why am I using depth images? Mainly because we want to make training feasible. For this training part, we want the algorithm to be feasible because, as I've mentioned, using monocular images involves lots of optimization, such as bundle adjustment, which are very time consuming. So training would be very long and we cannot see the results. So to look at the idea, we use depth fusion algorithms. So RL are reward driven algorithms. So we need to define a reward function. So so how do we encourage the agent to create a more complete 3D model? Because that's our problem. Before, the models that we are getting are very incomplete with large holes. So to have a more complete model, we got this metric from Eister et al., the one I cited before, the surface coverage. Very simple. The surface coverage is simply the number of observed points over the number of ground truth points. And our reward function is also very simple. We want until you get to the terminal surface coverage, so that's your end goal surface coverage, you will have four terms here. So the first term is simply the change in surface coverage. So that is positive because we want to increase that. Then we have a delta x here. We want to minimize this. That's why it's minus here or negative. And then we also want to minimize the number of steps. So every step or every number of input that it uses, we want to minimize that to make everything faster or efficient. So we introduce this penalty. But at the end of the day, what is important to us is to have a complete 3D model. That's why we have a reward of 100 every time it reaches the terminal surface coverage. So delta x is simply the distance traveled at that step. So for the training algorithm, an episode is defined as one scanning task for a particular target house. So in RL, we have episodes where the episodes are simply the sequences of states, actions, rewards until you reach the terminal states where for the most RL papers, they were working on games. So the terminal state would be the end or when you die your character dies or when you finish the game. For this case, the episode is defined as one scanning task for at one target house. So we implemented the very famous deep queue network for the discrete action space. And for the continuous action space, we explored and implemented the deep deterministic policy gradient or DDPG. So that's for ScanRL, and another contribution that we've presented here is Houses 3K, a dataset of 3,000 watertight and textured 3D house models. So we have 12 batches each with 50 Unix house structures. And each batch has 5 different textures applied on the structures. So for more details, you can look at our paper. But we also included there how we built this dataset of 3,000 house models. So these were manually built by our graphic designers in our team, in our lab. So they created design vocabularies, such as shown here. Then from there, they built modular pieces. And then they mixed and matched them to form houses, model houses. And so, yeah, so this data set was built modularly. And we also implemented some quality controls. So our idea is that this data set should not only be used by ScanRL, but for future research. So we made sure that that data set has a reach in texture, because that is important for, as I mentioned, in structure from motion algorithms, you have feature matching, feature extraction. So you want your synthetic environment to be realistic, to have a detailed texture. So how do we maintain that quality in the texture? First, we would sample from the batch and render in Unreal Engine. If it fails, for example here, it failed, a 3D model was poorly reconstructed, we would return the dataset to the designers. They would improve the ground truth texture to make it more detailed, as shown here. And that should be able to improve the output 3D reconstruction. So that's for ScanRL and Houses 3K. Now, how do we evaluate this algorithms? We proposed, or we presented in our paper, 3 experiments or 3 groups of experiment. The first one is the single house policy experiment, the one with the multiple houses and a non-house target model. So each experiment has different goals. So for the single house policy experiment, our goal was to test if ScanRL can train a policy to scan a house efficiently. So if you would notice, the ScanRL is the training algorithm as any RL algorithms. The output is the policy that learned the task that you want it to learn. So here, we want a policy that can scan a house efficiently, but can it really do that? No? So this policy tries to discover that. So how did we do it? We trained the algorithm or the agent on a house from batch 6 of houses. So basically, we sampled one house from our dataset, and it featured some occlusions like this one. And we set some terminal surface coverage, and we implemented both the discrete and continuous action space. And before I go to the real output or real valuation in numbers, here is an example. If you simply move around the house with fixed discrete action steps, you would have 87% surface coverage for 17 steps. Whereas when we trained this algorithm, if you would notice here, it was focusing on the occluded regions. By focusing on those occluded regions, it was able to achieve 97% surface coverage by 13 steps. So this is one sample of output that what we've seen from this idea. So based on this, we are able to show that this agent could learn something. But now the question is that we want to evaluate it further. So to confirm that this algorithm is not doing something trivial, we implemented more baselines, top, middle to bottom elevation. So you would see here a baseline that starts at the top, then bottom to the middle elevation. So basically, we are varying the order of wherein the drone traverses the elevation sets. Why? Because some models might be trivial, and working, for example, starting at the bottom could easily solve the problem. So we want to compare our algorithm to these different baselines. For example, here, middle to top or to bottom, then it would go to the top. So also for the third circular path, it starts with the bottom, then to the middle, then to the top. So from there, you would see that those baselines here. And for the discrete action space, our algorithm was able to do the same surface coverage with lesser number of steps. And for the distance, that is also true for the distance. So the rows here are the variations of the setup since this is discrete. So some setup only have 2 distance levels, 3 distance level. These are the resolutions. These are the elevation levels. And for both this all of this setup, our algorithm was able to find a better path with smaller number of steps or fewer number of steps and shorter distance. For the continuous phase, that is also true for the number of steps, but not for the distance. This could be caused because we are both optimizing the steps and the distance. And for continuous action space, it is more difficult to train an agent that does continuous action space. Now, another question that we had in mind is that can we use this algorithm to train a policy that can scan multiple houses? So that's what we really want. We really want to learn something. We don't want to memorize. We want our agent to be able to learn the real task of scanning a house. So, and if you truly learn that, you should be able to scan not just one house, but multiple houses. So that's the part here. And we also tested if it can be transferred to unseen houses. So that this experiment is shown here. After you finish one house, after this drone or this agent finishes the first house, we would change the house. So that's our training. So we are exposing the agent to multiple houses during its training. And we split the data set randomly or based on geometry. For geometry, we want to make sure that we want to check if it can learn novel geometries. But for the random, just randomly split the data set that we had. And for all of these cases, you would see that this agent was able to scan not just one, but at a high rate. For example, 217 out of 255. And for the test set, recall that these are those novel objects. And you would see here that it was also able to scan novel objects, 23 out of 25. So these are the solved houses. So what are solved houses? These are achieved 96% coverage in 50 steps. More details can be found in our paper. If you're interested, here are some samples. And lastly, I just want to show here another experiment, Stanford Bunny. We want to test if we can scan not just houses but also other objects. The same idea could be used for other objects, such as, for example, this Stanford Bunny. You would see here that it was able to reconstruct this using this data. So what are the key takeaways from our research? First is that we were able to present an idea, an algorithm that is learning-based to learn an NBV policy for 3D reconstruction for scanning in an optimal path, which is very important for large-scale 3D reconstruction using drones. We also showed Houses 3K, a dataset of textured 3D house models that we created to train and evaluate ScanRL, and the way we presented the way we developed this methodology, the methodology how we built this dataset. And some results we were able to achieve with fewer number of steps and shorter distance for the discrete action space. And ScanRL can learn to scan multiple houses one at a time. And it was able to transfer to scan houses not seen during training, except for some complicated batches. And we showed that this idea, this ScanRL, is not limited to houses and can also be used for other target objects. Of course, this is simply the first work that we did for this project, for this problem, and plenty of future work can be done, like complex scenes with more objects or houses is of interest to real-world applications, and creating algorithms that can be deployed to real drones with limited resources, and even robots is also a future work. And for if you are interested, you can look at our code and our paper, and the dataset are all available online. These links are also available in our paper. And again, I would like to thank Sony CSL Lab Paris for inviting me. If you have questions, I'm very happy to answer them. Thank you for listening.
Thank you very much, Daryl. It was a great presentation. Maybe I can start with one question. So correct me if I'm wrong, but the continuous space is more difficult to learn, and you couldn't get good policies for continuous space. Can you think of ideas of other learning algorithms which could be used to deal with the continuous space?
Yeah, that's very true. It's more difficult to learn the continuous action space, and it's still a problem in reinforcement learning. So there are lots of works right now that are newer or better than the one I implemented. So I've shown the DDPG. I think some on top of my head are TRPO, PPO. So you might want to look on those. I'm not updated if in 2020 there are new algorithms, but I'm sure that the current researchers are working to improve this problem for continuous action space. So
Okay.
It's really a challenge even for other RL applications.
And also, I have a question because I looked through your code actually, and I found out that the images you take are 84 by 84 pixels. So it's very small images. And I was wondering if we want to have larger images, do you think it's feasible? Because then you have buffers which are quite big. And do you think you need to modify the neural network to adapt to larger images?
Yeah, definitely. If you would apply this idea to real world. That's why it's a future work. You need to re-engineer the network architecture for that to work. Of course, this is a more simplified version, but you would have to look for um, some ways for your model to learn a more complicated setup. So yeah, you're right with that. You might have to re-engineer the network, the neural network there.
Okay. And then I have a final question, which is, could you see? I guess you visualized a lot of the trajectories that you get from your learning algorithm, and do you see some pattern of some tricks that the drone learns to scan houses?
Yeah, yeah. The agent learned uh, to first get close to the object. That's intuitive, right? So if you have a drone, or if you have the depth sensor, you want to get close to the object to have higher resolution. So I've seen that the agent gets close to that, and then it would go to those occluded regions. So it would go down to those occluded regions. I think I have some samples here. So this is a very common approach. You would see here, we start from afar, then it would learn to go near, then focus on those occluded regions. That's something that the agent learned in common.
Okay. Thank you very much. If there are any other questions, please. Yes, Peter.
Hello, and thank you for the very interesting presentation. Just a quick question, also maybe to follow up also on something on David's previous question. Is how, so you already seem to have like a language for houses, which is quite complete. So you've been able to test it on many different shapes. But how robust do you think the say the learning algorithm or the network that has been learned? How robust would it be if it came across an object with a very different shape? You mentioned that there's a strategy of taking an image from afar and then going closer. Would that be like a strategy that is very generic and that could actually be useful on different types of object?
Yeah, so for our experiments, those are the experiments I've mentioned. Yeah, so our data set have models that are varying in geometry, as I've mentioned. So yeah, so that's the variation that we've explored. And yeah, so that's our experiments were limited to that. So how robust it is to other set geometry, well, I can't say that right now, aside from the results that we have for houses 3K.
Okay, yeah, that's fine, I understand.
Thank you for that question.
Yes, Antonio, I guess.
Antonio, yes.
Yeah.
Well, first, thanks for the presentation. I have a couple of questions. First, what were the initial conditions of the training? I mean, about the position in the discrete training, because you have different. I mean, you could move incrementally in some set of fixed increments. I don't know if I explain myself. And what I want to ask is how many possible images can you get from this observational space? Because you have a defined set of movements, so it's not like you can move wherever you want in this discrete space. So there is a number of images you can get from that. I don't know if I explain myself.
Yeah, your understanding is is correct. You would have, since we simplify the setup in discrete action space, you would have a limited or fixed number of, or a finite number of possible raw images that you can render. Yeah, positions and images. So you can take a look at the table before, but we varied it to this discrete levels. So for example, some setup have 3 distance levels. So you can go from the farthest to the middle distance to the closest distance. Then we also have varying resolutions for the azimuth. So I think the reason why we are testing here, that's multiple, we have multiple rows here, is that we are varying those because, as you mentioned, depending on this configuration, you would have different number of or different possible discrete levels. So yeah, so those details are found in these results.
Yes.
Yeah. So.
Okay. Oh, sorry. And the initial position when you begin to train is totally random, or it fits in this increment?
Yeah. For our experiments, it's fixed. We fixed that to zero azimuth, 45-degree elevation to the farthest distance possible.
Okay. And one last question is like, how long did it take to train? Oh, how many episodes and how long? More or less. I'm curious.
It's varying, of course, because
yes, I mean, depends of a lot of.
Yeah, it depends on how easy the batch is. For if you have easy houses on that batch, it can learn easily. But if it's more complicated, it would fail most of the time. Like it would not be learning. Some failure cases would be the agent would simply learn to move forward and it would not be able to cover the object. So for those, I would say I'm using a very not really powerful machine. I'm using a machine. I think I forgot the GPU. It could be forgot the GPU, but it's just simply a desktop, a gaming desktop, and it would take me half. It's in my paper, the GPU. I think it's in the supplementary, and it would take me half a day to run in one batch of houses 3K.
Okay.
But it could speed up if you have better machine.
Okay. Well, thanks.
Thank you for that question.
Thanks. Yeah, that's all.
Okay. Any other question? Then if there are none, thank you again, Daryl, for your participation. It was a pleasure to have you.
Thank you also. It's an honor and a privilege to be invited by you guys. So very thankful, especially to David. Thank you.
Okay, thank you. And to the others, thank you for coming and see you next week, hopefully.